Hi. So the last video that we did described some more about waves, and towards the end of that video, we got to this slide that showed that the speed of a wave is equal to the wave's frequency times the wavelength of the wave. So V is equal to lambda f, or V is equal to f lambda is what it has down on the bottom of the screen. And then if we use the relationship between frequency and period's capital T there, the period is the time for one cycle of a wave, then we can also note that the speed of the wave is equal to the wavelength divided by the period. So kind of makes sense. The speed of the wave is equal to, well, how far one wave would travel divided by the time it takes to travel one cycle. So didn't say that the best, but the speed of the wave is equal to, the distance of one cycle divided by the time for one cycle, distance over time. Okay, that's what I meant. Close enough. All right. So let's see here. What do we have next? Got a little problem for you to think about. So we've got two kids here, Jimmy and Jenny. They're tubing on a river. And it's a quiet river until a speedboat goes by. It says that the two kids, Jimmy and Jenny, are 5 meters apart. So I guess 5 meters apart from each other on the river. The boat passes, and the two kids, Jimmy and Jenny, start bobbing up and down, and they bob up and down with a frequency of 0.25 hertz. And it says that just as Jenny reaches her highest level, there we go, Jimmy reaches his lowest level. And they are always within one wavelength or less from each other. So they're always, within one wavelength or less. So based on this information, we want to figure out the speed of these waves. All right. So one thing that I would encourage you to do is to actually draw a picture of waves and Jimmy and Jenny as you try to think through this problem. Pause the video, do that, and try to come up with a response before you let the video keep playing. So pause it. Okay, so what's the right response here? It's actually choice B. So let me give myself a little bit of room to work with, and we will see maybe why that is. Let's see if I start to draw a picture here. There's a wave. Okay, there we go. That's much more than I need, but that's okay. And it says just as Jenny, so we can picture Jenny being right here, reaches her highest point. That's Jenny. Use your imagination. And this is Jimmy here. Jimmy reaches his lowest point. Okay. And it says that these two kids are 5 meters apart. 5 meters. Okay. 5 meters. There we go. All right, awesome. Well, let's see. If I were to look at that 5 meters and think about how much of a full wave cycle is present there, I might notice that it's just half of a wave cycle. Let me explicitly draw in here a full wave cycle. Let's see. Full wave cycle. One way we can identify a full wave cycle is by going crest to crest. Crest to crest would be a full wave cycle. So that is my full lambda there. Okay. And if I look at that 5 meters, that 5 meters is only 1/2 of a wave cycle. Okay, so apparently, half of a wave cycle is the distance 5 meters. So if I rearrange this, that's going to tell me that my wavelength for this particular wave is 10 meters. And I'm told that the frequency is 0.25 hertz. Okay. And so if I put that information together, V is equal to lambda F, I will have 10 times 0.25. I will get 2.5 meters per second. All right. So one thing that you might be wondering about is the units there. I've got 10 meters times 0.25 hertz, and I end up getting 2.5 meters per second out of this. Yeah, I do. If you recall back to the last video, or maybe even the one before that, a hertz is 1/seconds. So that's exactly what a hertz is. It's per seconds. So 1/seconds. So the units do work out there. Okay, so everything that we've discussed in these wave videos so far is true for all waves. So it doesn't matter whether they're water waves or sound waves or waves on a string or a slinky or electromagnetic waves. It's true for all waves. We're going to get a little bit more specific about one particular kind of wave in the slides that are coming up. Specifically, we're going to look at waves on a string. All right, so we've got somebody's hand there. They're moving the string up and down and causing a repeated wave on the string. Doesn't have to necessarily be a repeated wave. We could just do a individual snap, a wave pulse. But the speed with which that wave pulse moves is dependent on, well, how kind of tight the string is. The tighter the string is, the faster this pulse is going to travel. And it also depends on how dense the string is, how massive it is. We could picture maybe trying to send a wave pulse down a really thin string, something like fishing wire, versus big old thick rope. And if we can imagine, if we make the same motion for a fishing line versus big old thick rope, it's going to travel a lot slower on that more massive rope. Okay, so the speed of our waves is really dependent on how tight the string is and how massive the string is. To put that into more defined terms, into a formula, into a quantitative form, we would use the equation right there down at the bottom. This says that the speed of a wave on a string is equal to the square root of the tension acting on the string divided by the string's linear mass density. You see the M and the L there. That's the mass of the string itself, not anything that's attached to the string, but the mass of the string itself divided by the length of the string. So typically when we talk about mass density, we use rho and we use mass divided by volume. So yeah, density is mass over volume, right? If we're thinking about density. Well, in this case, this is a linear density. So rather than a volume density, this is a linear density. This is mass divided by length. Okay. One other thing, we've used capital F there for tension because we already use capital T in this particular chapter for period. That the period is the time for one cycle. So we use the generic F for force, for tension instead here. All right. So we've got our formula. Let's do a little kind of easy example problem with it. It says we're looking at strings on a guitar, and we're told, well, specifically, we're considering two different strings, the high E string and the low E string. We're told that the length of both of these strings is 0.628 meters. Okay, maybe that wouldn't quite be true for a real guitar, but that'll work okay for example. It says that each string is under a tension of 226 newtons. Okay, great. And we're also given the masses of the strings. The high E has a mass of 0.208 grams, and the low E has a mass of 3.32 grams. All right. From this, we're supposed to figure out the speed of the waves on the strings. So yeah, find the speed of the waves on the two strings. All right, so hopefully the first thing that's jumping out at you is the fact that these two masses, that we've got them in grams. And we know that in physics that we use SI units. And so we wouldn't want these in grams, we would want these in kilograms. So if I'm going to just convert the high E from grams to kilograms, let's see, I would divide by 1,000. That's a bit cumbersome. Let's write that in scientific notation. And I get the mass of that string is 2.08 times 10 to the negative 4 kilograms. All right, that's great. And after that is taken care of, really, this is kind of just plug and chug. I've got my speed is equal to the root of tension divided by my linear mass density. The 226 newtons goes in for tension. The 2.08 times 10 to the negative 4 kilograms goes in for mass. And the length of the string there is 0.628 meters. That goes in for length. And then I just evaluate from there. So let's go ahead and do that. I'm going to cheat and flip over to the next slide where it's done already. There we go. And so we can see that for the high E string, that the speed of the wave is 826 meters per second. For the low E string, it's 207 meters per second. So yeah, I'd like to see if you notice anything about those two numbers that are there, those final results. 207 and 826. Yeah, okay. So you might have noticed that the high E is about 4 times the low E. As a matter of fact, if we'd been a little bit more careful about our numbers, we would have gotten exactly 4 times faster. And this has to do with harmonics, and that's not actually something we're going to talk about here in this particular video, but it's something that we may talk about coming up. Okay. We can certainly, if we want to listen to what a high E and low E are, we could certainly find other YouTube videos where we can go chase that down. And you might be interested in doing that. So yeah, I would definitely encourage you to do so if that's something that you might find helpful. All right. Guitars are great. This one is this particular problem is more of a kind of a well, let's put something together to so that we have an example. So let's talk about this one. We've got what, a 3-meter length of fishing wire that we've pinned to the ceiling. So we've pinned one end of the ceiling, the other end is free, and from that free end, we're going to hang a mass, a 1.2 kilogram pendulum bob is hanging from the string. We're told here that the fishing wire has a mass on its own of 2 grams. We also, I'm telling us that mass is negligible as far as its contribution to tension. So when we're concerned about the tension in this fishing wire, really the thing that's providing the vast majority of the tension is the mass of the pendulum bob hanging from the wire. We really don't have to consider the mass of the wire itself at all in that in figuring out the tension there. We could do that but if we do it, it really wouldn't add a whole lot of more accuracy in this particular problem, and it would add a tremendous amount more headache. I can't even stress enough how much more of a headache it would add. All right, so anyway, we've got this mass hanging from the string. What are we going to do? We're going to climb up a ladder to the top of the string and strike the top of it with a hammer. And when we do that, it's going to send a pulse down the string. We're asked how long it takes the pulse to reach the bottom of this string or wire. Okay. All right, so I think let's see. Let's do a couple things here. Let's first off, we notice that I've given us the mass of the string in grams again. So let's just fix that. 2 grams would be what? Would be 0. Hold on. Mass of string is 0.002 kilograms. All right, 0.002 kilograms. There we go. Maybe I need to make this thicker somehow. I don't know. I'll worry about that later. So the mass of the string is 0.002 kilograms. That bit of bookkeeping is taken care of. I think it would be helpful at this point to draw a picture. There's my ceiling. I've got this wire hanging down. I've got that mass hanging from it. All right. We can think about what causes the tension in that wire, and it's the fact that it's got this mass of the bob, because I said it's a pendulum bob, right? The mass of the bob hanging down, and so that we're going to have a weight force acting on this pendulum bob, and then upwards, keeping it in place, we've got a tension. All right, so the tension in that wire is going to be exactly the same size as the mass of my pendulum bob times G. So let's go ahead and fill that in. Tension in the wire is the mass of the bob, which is 1.2 kilograms, times G, which is 9.8 meters per second squared. And let's see, if I work this out, I get 11.76 newtons as the tension in my wire there. Okay, so that's the tension in the wire. That's important. So 11.76 newtons. So hang on to that, and we'll see what else we need to do from here. Let's grab an eraser and go to town. 11.76 newtons. And let's see, this part of the problem's done. We'll keep that one in mind. And now we're going to, what are we going to do here? We're going to just go ahead and pull out our equation for speed of a wave on a string. V is equal to the root of tension over my linear mass density for the string, and plug in my values. So let's go ahead and do that. So V is equal to the root of my 11.76 newtons divided by the mass of the string, 0.002 kilograms, there we go, over the length of the string, that's 3 meters. All right, and when I evaluate this, as long as I don't get numbers crossed up in my calculator, I should get something that looks like 133 meters per second. Okay, all right, so great, good. Now what? Well, let's see, we've got this wave pulse that's happened right here. It travels down this way, gets to the bottom. We're wondering how much time it takes. Well, it has to cover a distance of 3 meters. And we might recall that speed is equal to distance over time. If we rearrange that equation, we can see that time is going to be equal to our distance that we have to travel divided by the speed. And when we plug that into a calculator, we should get out the result that it takes 0.023 seconds for this pulse to travel down to the bottom of the string. All right. Thank you for watching.